Hello, welcome to this video. In this video, we're going to cover two examples of performing goodness of fit tests. And remember, goodness of fit test is a type of hypothesis test that applies to categorical data. So let's get to the first example. It's called crooked dice. We roll a standard, and let's highlight this. Because it says standard, that means we're assuming it's fair, right? So we roll a standard six-sided die 60 times, and we record the outcomes. So notice that there's a range of possible outcomes for what happens when you roll a die 60 times. It could be on one extreme that you get 60 ones. It could be that you get 59 ones and, a two, right? 58 ones and a two, two twos. So there are many possibilities for the outcomes, right? And each outcome corresponds to a distribution of the 60 rolls. So for instance, if I were to write the distribution or draw the distribution describing this first outcome, it would be 60 and then 0 all along. If I were to draw the distribution representing this second outcome, it would be 59 and then 1 and then zeros over here, right? So each outcome corresponds to a different distribution. What we want to do is test whether or not this particular outcome, right, the outcome that we get from this experiment, whether or not it is statistically significant, how different it is from the expected outcome. So the expected outcome, right, another way to say expected would be the theoretical outcome. If you roll a fair die 60 times, would be, right, it would be like you'd get 10 ones, 10 twos, 10 threes, right? So forth and so on. So depending on whatever we get, how extreme is it compared to what we would expect or the theoretical outcome, okay? Testing this is going to start off with creating your hypotheses, your null and alternative hypothesis. So the assumption of null alternative is always that things are okay, things are what they should be, things are as stated, right? So it would be that the die is fair, i.e. this is our distribution. Alternative hypothesis, the die is not fair, right? And it's due to more than just, it's randomness that comes from sampling. Okay, so first thing we do is compute our observed versus our expected frequencies. This is the data that's given, and this, of course, is a distribution. So we could draw the distribution, right? 1, 2, 3, 4, 5, 6. Excuse me, the height here would be 12. This would be a little 13, a little higher. This would be 8. Sorry, 6. Sorry, 16. And then 5, right? So this is essentially our sample. And then the expected is, of course, that everything's going to be 10. Okay, so the expected for each of these is going to be 10. How did we get that? Because we're assuming that the die is fair, and we have 60 rolls, and we have 6, possible outcomes. We are back to a uniform distribution. So remember, we studied these different types of distributions: uniform distribution, Bernoulli, binomial, Poisson. Those were our discrete distributions. And then we studied continuous distributions: exponential, Gaussian, t-distribution, and chi-square distribution. So uniform distribution is appearing. Why did we study those distributions? Because they're helpful when we're modeling situations and, trying to perform hypothesis tests and tests for inference. Okay, so next thing we're going to do is compute our test statistic. So in terms of the steps to hypothesis testing, first thing is you set up your hypotheses, your null and alternative hypotheses, check out which one is the claim. Second thing is you're going to choose your alpha, which is the tolerance for a type 1 error. Third is going to be look at your sampling distribution and your test statistic. Fourth is going to be see how extreme your test statistic is compared to the assumption that the null hypothesis is true. And to measure how extreme it is, we've got two approaches. Number one, we can look in the critical value and rejection region approach. The second approach we can use is the p-value approach, where we compute the probability that we would get the sample that we did given the assumption that the null hypothesis is true, right? And then if that's a really high probability, we fail to reject our null hypothesis. If it's a really low probability, then we reject our null hypothesis. That's the method that we'll use today. So we are starting off and we're going to compute our chi-square test statistic. And here's the formula. So it's the sum of the squared difference between your observed and your expected divided by the expected. So for here, we said expected is 10, right, for each of these. So then this is O is observed, E is expected. So I could say, what is O minus E? Make a table, so that'll be 2, 3, -2, -4, 6, -5. And then I can look at O minus E squared. Sorry, let me make this a little better. So O minus E squared, that'll be 4. That'll be 9. That'll be 4. That'll be 16. 36. Remember, we were talking about how squaring is going to minimize small differences, and it will dramatize or expand or maximize large differences. So this difference of 6, right, now turns into 36, right? So that's the kind of expansion that we're hoping. Let's go and divide everything by E. Remember that we need to divide by E. So if I divide by E, that's 4 out of 10, 9 out of 10, 4 out of 10, 16 out of 10, out of 10, out of 10. So this would be 0.4, 0.9, 0.4, 1.6, 3.6, 2.5. And then the last thing we do is sum them all. So the sum of O minus E squared over E is going to be the sum of all of these terms. And that's exactly what we have here. We'll end up with 9.4. So our test statistic is 9.4. How big is that? How do we know right, like what that is? Well, let's take a look at our chi-square distribution. We know typically a chi-square distribution looks like this. We know chi-square distribution isn't going to have any negative values, right? But we also know that the chi-square distribution changes based on the degrees of freedom. So for us, the degrees of freedom will be 1, 2, 3, 4, 5, 6. Our n in this case is 6 because we have 6 categories. So n minus 1 will be the degrees of freedom. So this tells us that we're looking at a chi-square distribution with n or 5 degrees of freedom. So let's go to our applet. And I'm going to see if I can airdrop this page. Perfect. Okay. So here's our chi-square distribution. Degrees of freedom, we're going to put 5. And as soon as I do that, I get a sketch of my chi-square distribution. Do you remember my test statistic was 9.4? So I'm going to put in here 9.4. When I do that, the definition of extreme in the case where we're looking at comparing distributions is determined by having a larger test statistic. So anything to the right is more extreme. Why is that? Because remember, we're looking at the difference, the squared difference between what we observed and what we expected. So a more extreme sample would be a sample that has larger differences between what's observed and what's expected, which means your R value is going to be larger. So the pink area here actually gives us our p-value. So 0.09413. Right? So notice here, so we used a tablet. Did we get this with a 0.094? Oh, let's see here. We said that was 5, and then that was 9.4. Yeah, okay. So we got 0.09413. Now notice in their computations, they did 1 minus the area to the left. This area to the left is what you get if you're using the CDF, right? Because the CDF is going to compute the area from minus infinity up to that value. So if we want the area to the right, that's the same as 1 minus the area to the left, because the total area under the curve has to be equal to 1, right? Remember, that's the golden rule, one of the 2 requirements for any distribution. Okay, so the area, that probability that you would get a value or a distribution as extreme or more than the one we got, assuming that the die is fair, is about 9.4%. Okay, which is what we get here. And so, just taking, so basically, from here we see, oh, alpha is 5%. We got 9.4%, and we failed to reject. Now, if alpha were 10%, then we would reject. So we say there's enough evidence to say that it's not true that the die is fair. But at the 5% level, we don't have evidence to reject, which means, yeah, with these observed values, they're a little off from the theoretical distribution, but they're not so off that it causes us to question whether the die is fair. Okay. Okay. Yeah, so not enough evidence to say the die is unfair. We'll put here at a 5% level. Right. Okay. So any questions? So just to kind of summarize here, what do? We had to determine the hypotheses. Then we had to figure out our alpha. I like to put that as step 2. If it's unsaid, we can assume alpha is 5%. Okay. Next thing we did is we have to consider our distribution and our test statistic. In this case, we have a chi-square distribution, and the key is the degrees of freedom should be the number of categories minus 1. The formula for our test statistic is going to be the sum of the squared difference between our observed and our expected over E. So we have to figure out what's our test statistic, what is our distribution. This distribution is assuming that our null hypothesis is true. So for the goodness of fit test, your H naught is that there's no difference between your expected distribution and your observed distribution. And the alternative is that there is a difference. Okay. So once we have our test statistic and our distribution, then we have to make a decision. And that's going to come from either critical value and rejection region, method, or p-value. For us, in this case, the p-value is going to be the integral from your r to infinity of whatever is the PDF for your chi-square distribution. Yeah, which is going to be based on your n minus 1. So this is the area to the right of your test statistic. And I'm putting it like this because this is how the textbook describes it. And it's going to involve a gamma. You'll have like a coefficient out here, like it's 1 over gamma, k plus 1, or something over 2 or something like that. And basically, computing this integral probably is going to be, it very well could be too complicated or too long, involves lots of integration by parts. So You can estimate it. Yeah. So you can just either write down the exact value, which is the integral, you can estimate it. How to estimate it? Use a table, use an applet, use a calculator. Yeah. And really, an applet is just a calculator, right? So a table or a calculator. Okay. When we're looking at the critical value rejection region, you find the location on the horizontal axis that results in the area to the right equaling your alpha. So in this case, we would want the area to the right to equal, oh, okay, the cutoff is 11.07. So if we get a test statistic that is larger than 11.07, then we would reject. And our rejection region would be anything greater than 11.0705. Okay? So this is the graphic that demonstrates the critical value / rejection region method. The flip side of that is the p-value method, which is where we had the 9.4. We said, oh, okay, there's 9.4% chance that you'd be greater, 9.4%, not too small, so we fail to reject. Both methods lead you to the same conclusion. And then lastly, you make your decision and interpret the results. And we kind of bundle that up in this scenario because we bundled it up into one because we said, okay, this is our conclusion. This is our decision. So decision, don't reject. The conclusion, not enough evidence to say that the dice is unfair. Okay. We're going to use this same framework to do the next example. Next example is a little harder because we'll have a different distribution that we are comparing our observed distribution to. Okay, so this is a biology example. I think this was in the book or similar to something in the book. And I'll let you read it. I'm looking at genotypes and phenotypes. So here's the bottom line. Sorry. Here we go. So the bottom line is we have this distribution and we are expecting to have this ratio of 9 to 3 to 3 to 1. So notice this is not uniform. This is not a uniform distribution. Okay, so if we have a total of 55 observations and we are expecting a 9 to 3 to 3 to 1 ratio, how do I determine the number of expected of each phenotype? Well, altogether, 9, 10, 11, 12, 13, 14, 15, 16. So altogether we have 16. So 9 out of 16, what percentage is that? So that's 56.25. So 56.25% should be purple. 20%, 3 out of 16. So 18.75% should be tall and white. 18.75% should be short and purple. And then 6.2%, 6.25% should be short and white. So to calculate the expected number of tall and purple, I need 9 out of 16 times 555, right? So I need 300. So I'm expecting 312.1875. Well, you can't have, that's not like a true number. So I need to round this up to 313 because I'm expecting a little bit more than 312 of these. So I'll round it up to 313. Let's do this with this 101. So I'm expecting about 19%. Sorry, I'm expecting about 19. No, I did this incorrectly. I need 555 times 0.1875. So I'm expecting about 104. 6. So that 104, we could leave it as 104. Sometimes it's kind of tricky because if we round up on every single number, then this total here could end up being different from this total here, which kind of messes things up. So, but for now, let's go ahead and we're going to go ahead and 10 and just follow the rule of thumb to round up for everything. So that'll be 105 as well. And then what's my 32? It'll be 0.0625 times 555. So that'd be 35. Okay. And honestly, probably I would have that as 104, 104 because those are so close to 104, but the difference is negligible. Okay. So we have our expected values, and now we compute. Yeah, okay, see. Yeah, so I did do the 104. So we'll do the 104. That should be, I'm gonna challenge that. That should be 313. Okay. The difference here is small, so it'll be it'll be close enough. Close enough so that the R let's see here. What is the R going to be? Plus 0.51, so change this to 0.510. That's our R. And what about our distribution? Three. So if we go back here, chi-square, we're looking at 3 for our degrees of freedom. And the x we had is point. So this is our, so our distribution here is going to be 0.5. Our distribution is graphed. Our chi-square distribution is graphed. We are looking at a test statistic of 0.5103. And the probability that we would get something as extreme or more extreme is 91%. So in other words, we interpret this to mean, you know what, almost all of the time, or most of the time, 90% of the time, we will get values that are more extreme than the ones we did. So we are certainly failing to reject. This is a big P. Right? So we're able to make our conclusion, not enough evidence to say that the traits deviate. Okay, all right. So let me know, as usual, if you have any questions about how any of the content in this lecture.